Okay, right. Good afternoon, everyone. Welcome. Anyone who doesn't know, I'm Sam Thompson. I'm the Graphics and Communications Manager here at Webtec, and yeah, thank you for joining us. Our first webinar, which this has been something we've been aiming to do for some time, and with the most recent updates to Teams it's made it a lot easier for us to do it. So we've been looking forward to doing this for the last 6 weeks. This is a webinar based on, as you know, it's on hydraulic flow monitoring, and it's presented by Martin, our managing director. So just a few housekeepings. I'm sure everyone's already on mute, so that's great. But if you could just keep on mute during the during the recording. There's a chat or there's a Q&A function on here. So if there are any questions you've got, then please feel free to put them into the Q&A or the chat, and I'll keep an eye out for them and ask them on your behalf, or at the end of the session, if you feel free, unmute yourself and ask the question yourself. But I will keep a look at that during the session. Just skip on the slide line, please. So just a few things from me before we start. Make It Blue, for hopefully everyone has at least heard of Make It Blue. It's our unique. It's our 4-step process that envisions the whole company, and we work to that to provide and maximise the potential of hydraulic machinery without the complexity of costly consultancy. That's our official line, and we break it down into 4 sections, which is begin, listen, upgrade, engineer. Martin will touch on this again in the presentation, but this sort of really fits into the begin part of that, where for many years we've strived to create as much educational and informative and thought-leading material as we can, from videos to white papers to case studies, application case studies, all that good stuff, to just become a resource really for everyone, and to hopefully provide useful information. So this really fits under that, and this was the bit that we were kind of missing, and we hadn't really delved into this kind of the way of sharing this information, rather than just putting together a PowerPoint and just sending it out. So that's kind of where that fits in the sort of ethos of the company, and we have an aim. We've set ourselves a target to do 4 of these this year. We've got experts and a lot of people to help us, or ideas that we would like to work with. So we're aiming, again, February, we're kind of earmarking our next one. So I will put more information out in the future regarding that. So that's kind of our aim for this year, is to really push on with that and to create other content. We've got articles and white papers that we're writing at the moment, and other ideas. So hopefully we can keep publishing more for you. And just a brief one more thing before I go on. So we also have a book. I don't know who is aware of this, but Steve Skinner, along with Martin's help, wrote the Introduction to Practical Hydraulic System Maintenance a good few years ago now, and it's an introduction to hydraulics. This is available. It's on Amazon to buy. It's all the proceeds go to supporting STEM projects that we help with. So the Arkwright Scholarship, primary engineer, and things like that. So have a look. As I say, all the money goes towards that. We invest it all back into that. But it's brilliant. It's extremely well illustrated and written. So hopefully that would be of use to some of you, if not all of you. And then just one final part, Martin, if you could skip on. Comes through, and just to I'm not going to do it individually, but we have an extremely good, fantastic distributor network. So after this, if there's any thoughts, ideas, problems, questions you have, then you can find our full list of distributors on the website, which is there. I will share that link with you afterwards as well. And just below is the sales and marketing team here at Webtec, which cover all the offices and companies across the world, including me. So I just wanted to highlight that as well. Anything I've mentioned here, I will at the end. I will email everyone. We've got a survey that we'd really like if you could fill out. Feedback is really important, and I will include all the links to all the stuff that I've just talked about there. So yeah, so that's all from me. Just a rough introduction, and I'll pass over to Martin.
Thank you very much, Sam. Yeah, so as you're aware, this talk's on innovative hydraulic flow monitoring. And this is a talk that we put together about 6 months ago, I suppose, for the IVT, the Industrial Vehicle Technology Show in Cologne. And then we gave a similar presentation in Chicago to the IVT there in August. But at the time, it was a relatively select audience that got to see that. You had to be attending the show in person. And I think in one case, you had to spend quite a few hundred pounds or euros in order to actually have access to the presentation. So we thought it was appropriate to share this out to a wider audience and really talk about how we believe flow monitoring is kind of the missing link in condition monitoring on mobile machinery. So just a little bit of background about Webtec. As you can see across there, we've got Make It Blue, and Sam's just alluded to our four-step process there. Webtec, hydraulic measurement and control company, we're coming up for 60 years old. Got about 70 employees, the majority of whom are employed in the UK where the manufacturing is. And then we sell through sales companies onto distribution. So our sales company is headed up by Matt in North America, by Patrick in Europe, by Mark in the UK, and by Vivian in the Far East. And so that supports our distribution network, which has enabled us to reach many customers worldwide over nearly 60 years. And if we look at the process that Sam's just talked about, we're beginning here with a bit of information sharing, and that's been an ethos of ours for many years, going right back to people looking at screw threads and the like. How do you convert BSP into SAE on our website? And as Sam's mentioned, lots of white papers and books that we've done since then. And then going through the sort of listen, upgrade, and engineer. And really, the talk today is based on a lot of information that's come from speaking to customers, particularly over the sort of last 6-7 years, and listening to their challenges in the mobile machinery industry, on the on and off highway machinery industry, and taking what at the time was a standard product for industrial hydraulics and converting it, adapting it, modifying it to make it suitable for the much more arduous conditions that our customers were telling us about, where instrumentation wants to be mounted permanently on a mobile machine. And really this process started about, I think, 2016 with a particular customer. 1 or 2 customers at the time. Has expanded into about a dozen customers now. We're working in depth with on this particular product. So we started off really with a turbine flow meter. Many of you will recognize a product like this. This particular one is a milliamp turbine flow meter, measure flow and temperature. If you screw a pressure transducer into that test point, you're also measuring pressure. And that typically would have been used, or still is used, on a test stand for testing maybe valves or pumps. Typically used as a reference to tell you what the flow in and flow out of the particular hydraulic component is, but often in a very benign environment. So the test stand will be heated, the environment will be probably 20-25 degrees C. Won't see much shock, much vibration, will never get rained on, it won't get dropped. And generally that sort of device will sit on that test stand quite happily 20-30 years without a problem. The duty cycle may not be particularly high, so it might only get used for a few hours a day. A very reliable laboratory-like instrument. And the challenge really we've had this first customer that came to see us, who was in the utility industry, saying, okay, so I want to put something like this and I want to put it permanently onto a machine which goes in really the opposite of that sort of environment. It's an environment where it's being driven around for 12, 14 hours a day, where it's going to see massive shock, it's going to see vibration, enormous temperature swings, both in the hydraulic system itself and in the atmosphere. It could get sprayed with salt and sand, and generally it's a horrible environment, and a long way from the sort of benign environment that you'd see on a lot of industrial test stands. And so talking to these customers, we started to collate really what the challenges were for them and why they thought it was important to monitor their hydraulic system. And the challenges really could be summarized into those 6 titles that you see on the screen there. Downtime, top of the list really for all the customers we spoke to, was how do we minimize unscheduled downtime caused by hydraulic failures on the on and the off highway mobile machinery. But beyond that, people were sort of saying, well, downtime, sure, we want to prevent it, but what about what happens beforehand? So what are the early indicators of that, or how do we know if the efficiency of the machine is going down? So cycle times was another area where you're saying it's quite difficult to see if the machine is operating 5% or 10% slower, but we really want to know if that's happening. In the same way, if a component breaks, how do we minimize the warranty cost on the machine? And how can we tell whether it was something that the customer did or something that was a failure really, or a flaw in the component that we fitted on there? So how can we look at what was happening before the component failed? And maybe around that same area, one of the questions that was posed to us was, well, what happens if we just want to go and charge the customer for using the machine, not on the amount of hours that they had it for, but the amount of hours that they were actually using it for, or how much power they were actually pumping through that system. So we sort of collated all these things together. Energy efficiency, clearly we live in an industry where we use a lot of energy, very power intensive industry. How can we reduce the amount of fuel that we're burning? In terms of control, there are some customers saying, well, if I've got an actuator and I'm feeding a certain amount of flow to it, how can I be sure that it's actually operating at 30% of its range? How can I be sure that it's delivering exactly the flow that I want it to be delivering? What's that feedback loop? And the last category, and perhaps the most important category of all of these, was how do we improve the safety on these machines? How do we remove operators from the dangerous parts of the machine and still achieve the other things? So how do we achieve reduction in downtime without a service engineer having to put themselves in danger? So what I'd like to do over the next sort of 20 minutes is really expand on each of those and start with talking about downtime and what are the areas that flow can help in reducing downtime. So if we look on the other picture here on the screen, just a couple of examples of industries which our customers are working in. So one around agricultural attachments, the other one around municipal vehicles. It could equally be applicable to mining machinery. The message that's coming to us from the customers is saying, well, do you understand how important it is that we minimize downtime? Because the cost of us not being able to put compost onto the field or harvest the field at a certain time isn't just the cost of repairing the machine, but there's also an opportunity cost of not getting that work done at that particular time. There's a cost of the labor to actually repair something or to bring spares in. And customers are telling us really for a municipal machine that could cost around about $15,000 to $20,000 a day. If it's in mining machinery, then we could be looking at sort of $50,000 to $70,000 an hour. And so there's really quite eye-wateringly large costs associated with downtime. So I guess the question really to say what's flow monitoring got to do with all of this is to look at a little example here of a pump, a very simple circuit, 100% efficient pump that's going to deliver 100 litres in order to lift up this weight on a cylinder. When we switch the pump on, it starts lifting the cylinder up, running at typically 60 bar and takes roughly 5 seconds to lift. Now in most hydraulic circuits, we would be monitoring temperature because it's very easy and cheap. We'd be monitoring pressure because it's also relatively cheap to do and it's non-invasive. But if the pump then starts to deteriorate and it's maybe only 50% efficient. It's only delivering 50 litres from it. When we switch the pump on, it's still operating at 60 bars. So if we're monitoring the pressure on the system, we can really see nothing wrong with it. We might be measuring the temperature on the system, and we can also see that it's operating at sort of 40, 50 degrees C that we might expect for that system, but that also not giving us any clue. The only clue really that we've got an inefficient pump is that it's taken us twice as long to lift that weight up. And so unless you're measuring the stroke time, there's no real way of knowing that you've got a problem. That is, unless you're also measuring flow. So for many people, that's not really been an option because they considered it too difficult or not available or too expensive to do, and people have relied on using proxies in order to see if there's an inefficiency in the pump. If we look at the different maintenance opportunities that exist for a customer, most customers these days will attempt not to run breakdown maintenance. I don't want to run the machine until it's broken and then go, right, I'll go and fix it. Really, the cost of that is enormous. And so the most appropriate way, really, if we're not offering breakdown maintenance, is then to considering other approaches like preventative maintenance. And on this graph here, you can see that the pump's performance sort of deteriorates very slowly over time. And you have to make an estimate at what point it would make sense to remove the pump from the circuit before it breaks. And if you were to do that in the middle line here, then you would effectively have wasted half the life of the pump. If you did it and you got the timing just right, and you did it on the ideal replacement time, you would have maximized the life of the pump. Of course, the challenge is that if you didn't do it at ideal replacement, it says, no, I've got another couple of years in that pump. Chances are that the pump would suddenly have catastrophically failed, and you've overestimated the life of the pump. And if the system is repeatable and the application is under the same conditions all the time, then that preventative maintenance is arguably a good approach. And what you might typically do is use one of these tools that we manufacture. Other people manufacture similar sorts of products for either a portable hydraulic data logger or a tester, where you would periodically test the machine to see how well it's doing. So in this case, this example here, they're testing an attachment on the end of an excavator, but you could equally be testing the actual pump output from the excavator and really comparing it to the factory settings and say, okay, how well is it performing now? What's the efficiency of that pump now? And so doing those tests will tell you whether you've got some pump wear happening, whether you've got insufficient flow coming out. It might also show whether you've got excessive flow through the drain line, which could be increased leakage across a particular component, or you could see a mismatch between the actuator flow rate and the speed, which means there could be some loss of volumetric efficiency. And typically, as you can see in this example, with a man with his hand on the loading valve, is you would do this when the machine isn't actually doing any real work, and then you would simulate the work by restricting the flow using the loading valve and increasing the pressure and seeing what the impact was on the flow rate. So in principle, this approach has worked very well for many years. The only downside of it is that, well, two downsides. One is you can only do it periodically. These aren't permanently installed devices, and so you have to pick and choose when's a good and appropriate time to test. And the second one is that you have to actually break into the circuit in order to do that, which could have some risk of introducing contamination. But if you were to carry out a test like that and then sort of plot it like we did before and say, okay, I've got my pump over time, I'll put a dot on it and say that's what the performance level is now. In itself, that one dot on the graph doesn't tell you very much because you don't know whether that's good or bad. So you would perhaps go and pull out some data from the manufacturer of that pump and say, well, what was it doing the day it left the factory? And what was the performance level then? And so you could plot the new pump performance level where we are now. And you might also then estimate a certain volumetric efficiency. That's when we should really change that pump out, and that's the allowable degradation in performance of that pump. we can plot that. As engineers, we love plotting plotting lines and extrapolating them. So we can say, right, that's where it was. The first red dot is where it was when it was brand new. This is where it is now. I think you can probably guess what's going to happen next. I'm going to say, okay, in the future, if the future is just like the past has been, then that line will just carry on declining at roughly the same rate. You can extrapolate that out and say, okay, if it's 2 years since we fitted that pump, in another 2 years, we should really change the pump out, because at that point it's going to use most of its good life. It will have worn to the point where we go, it's probably not safe to keep it in there any longer, and we should replace the pump. Of course, that assumes that the environment and the situation that we're using the machine in is repeatable, and that the operator is repeatable, and what's happened in the past is a good indication of the future. But there's always a chance, perhaps a high possibility in certain industries, that really you could get rapid pump deterioration. And so if you test the pump once every couple of years, you're going to miss that point when you suddenly get a real change in the gradient, and it's going to deteriorate very quickly, and leading to catastrophic failure. So the step really above doing preventative maintenance would be to move towards more sort of predictive maintenance and condition monitoring of the machine in real time. And so in the same way, we can say, what does the new pump performance look like on the machine? We can continuously monitor that, because the flow meter essentially could be on the machine all the time. And as we can see here, if the performance suddenly starts to degrade really quickly, that can be the trigger, that can be the signal to say, okay, let's stop the machine, let's schedule in some maintenance, and let's take that pump off. And that, if you like, is the rationale for putting the flow meter into the circuit, and really monitoring the output, in this case, of the pump in real time. And the way that would work, and the way a few of our customers are using it, would be to then link that flow meter to the machine. In this case, we've got a CAN bus connection to it, and then feeding the signal out from the machine onto the bus that's already on the machine anyway, transmitting that data to the cloud, and then enabling, using the software that's often already in place for the OEM, to view the current performance and maybe activate some triggers to say, okay, this has suddenly happened, this is something that you should have a look at. And ultimately to try and predict problems before they happen. So we just look at the CTA flow meter that we've just been seeing in that example beforehand. So this unit here looks similar, but as you'll notice, a bit different to the first flow meter that I showed right at the beginning of the presentation. The other one had been designed very much for industrial application. This one is what's come about through that begin, listen, upgrade, engineer process with the various OEMs that we've been talking to, where they've talked to us about their challenges, not just of downtime, but how do you actually install a sensor like this onto a machine, talking about it's got to be as short as possible, it's got to be as light as possible, it's got to be as robust as possible, and that's brought about various changes to the design. This particular unit here is rated to 300 litres, but there are lots of different sizes that are possible. Perhaps the most important acronym on the screen there is IP69K. You may not be familiar with the IP standard, but effectively that's pretty much the top of the range in terms of resistance to contamination, particle dust ingress and water. The other thing that the customers were saying to us were, we don't really want to have milliamp or 5 volt. We want to have CAN bus. We want a digital signal coming out of this. We want to feed more information than just flow. It's also feeding temperature information onto the bus, so that they could use that information along with lots of other information they've got on the circuit to give a better picture of how that machine is working. And the CAN bus has clearly lots of other benefits. It's faster data exchange. It's got bidirectional comms. It multiplexes, so we can feed multiple signals. It's got higher resolution. it's got error checking. So the change, if you like, from an analog output to a digital output clearly has some benefits as well. There are customers out there saying, well, I don't have CAN on my machine. Could I have milliamp? Absolutely, we could do a milliamp version, but the majority of the customers we've been talking to have wanted to integrate this with their CAN bus. Just a quick look at how such a sensor measures flow. I suspect for many of you, you'll be familiar with the principle. But essentially, as flow goes through, it rotates the turbine blade. That turbine blade, the frequency of it is picked up by a pickup that goes into a circuit board above. There's some clever electronics there which are smoothing that signal, which are linearizing that signal and turning it into a flow rate. And as more flow goes through, the turbine turns faster and gives a greater signal. The advantage of a turbine flow meter over other technologies, and we operate 2 or 3 other technologies, is that the pressure drop is relatively low, and therefore, when this is permanently installed on a machine, you're not wasting much energy in order to measure the flow. In terms of the signals coming out, the sensor that you can see pointed to there is also measuring temperature. So we're measuring the fluid temperature and we're measuring the frequency of the turbine, and hence we know the flow and the temperature. Some customers, or the majority of our customers, have already got some sort of pressure measurement on the machine, haven't wanted to measure that in addition here, but pressure could be added into this, so you had flow pressure and temperature coming out of the same device. Compared to a conventional flow meter that I showed right at the beginning, as I mentioned, it's smaller, it's got completely new electronics. Because of the massive temperature swings, we've had to move to military grade components in order for it to survive the high operating temperatures, the high fluid temperatures, different housing to survive the dust, the salt, the gravel, whatever it's that's thrown at it on a mobile machine. Shorter body. Overall, the pressure drop on this unit at 80 gallons at 300 litres is less than 1 bar, less than sort of 15 psi at 300 litres. So energy losses really are relatively small for this design, and with the intention that this is fit and forget. The only proviso really for this sensor is that the oil is kept to a reasonable level of cleanliness, but that's really required anyway for most of the mobile machines because the pumps themselves demand it. In terms of where this is being used, so there's some examples on the screen there of hard rock mining, municipal machinery, agricultural machinery, quarrying, plus we have a couple of test beds that we're using. We've been working with the National Fluid Power Centre, who have been testing the unit. We've also got an IoT demonstrator that we've been building and developing with Premium, just to demonstrate the whole cycle, if you like, from collecting the information to sharing it onto a dashboard. So that's a look, if you like, at the downtime side of the flow monitoring in the CTA. There were 5 other things that we mentioned at the beginning, 5 other challenges that people had on the machines. I just want to go and touch on those now. So monitoring machine cycle times, got a number of customers who are also looking at autonomous vehicles, and clearly when you haven't got a human being actually on the machine, you've lost those senses of hearing and feeling and touching and smelling what's going on with the machine, and you need a replacement for that to say, how is that machine actually working? And so monitoring whether the machine's sort of 5, 10, 15% slower than it should be is really important. If the machine's rented out by the hour, you have an estimated job cost by the hour, a 10% degradation in the performance could mean that the job takes 10% longer, and actually your operating cost has gone up accordingly. Just reminding us of how that might work. So the flow meter is installed permanently on the machine wired into the CAN network, goes to a gateway, and then transmits through that gateway to an IoT terminal, and then onto some kind of dashboard with analysis to tell you trigger when there's a particular problem. This health monitoring, some of the conversations we've had were around not just the selling of the machine, but also how do you then offer a customer service to the operator afterwards, whether that's a rental machine or a machine that they own, to say this is how the machine's doing. This is what you need to be preparing for. Do we need to start thinking about getting spare parts in because we can see that this machine is going to fail, or this particular component is going to fail soon? Everything really in order to shorten that lead time when it comes down to doing some preventative maintenance. Clearly, for many OEMs, they want to make sure that if a component on a machine does fail, that they understand why that happened, and they don't want to have any higher warranty costs than absolutely necessary. And so the idea of understanding what happened on the machine before something failed is really useful. If you're measuring flow and you combine that information with pressure, then you've very rapidly got some information about power on the machine. If the machine is then being used in different environments, maybe different rock surfaces, different earth, then you can tell by the amount of power it's consuming how hard that machine is working. And how hard that is working can feed into the wear on the machine, and could, as I mentioned at the beginning, for some customers mean that rather than saying we'll rent the machine by the day, we'll rent it actually by the number of kilowatts of power, for example, it's consumed, which is perhaps a fairer way of looking at wear and tear on a machine than just the number of hours that it's been rented for. So efficiencies, mentioned it at the beginning, this constant drive to improve the efficiency of machines. If you wanted to look at the volumetric efficiency of this particular hydraulic drive motor, that combination of knowing the speed of rotation and the displacement gives the theoretical flow through that motor. We can also measure the actual flow rate, and we can measure the volumetric efficiency, and that gives us the best indication possible, really, of the health of that motor. Again, telling us whether we can expect that motor to survive for a long time, or whether we should really be planning some scheduled maintenance in order to switch that unit out. In a similar way, if we're looking at the output of the pump that's driving a whole machine or a whole unit within a machine, if we look at the hydraulic flow and pressure, we know the power output. And if we knew what the power was coming in, so whether it's the speed of electric motor or diesel engine and the torque that it's generating, we can look at the overall efficiency of the machine. And certainly from an R&D point of view, many engineers these days are looking at how can they improve the overall efficiency of the machine. Clearly having onboard flow monitoring is a big step towards really understanding the total ins and total outs in terms of power. There's an interesting application that had one customer talk to us about, and that is, if we have a proportional valve delivering a certain flow rate, how can we be sure that that's the flow rate that we're actually getting? And there may be reasons, for example, a particularly harsh environment, why we can't put sensors on the motor itself, but instead we want to monitor the flow rate being fed to that motor, and then feed back that signal back to the controller, and use that closed loop control to get really optimal control of, in this case, a winch. Particularly relevant here because you see the diameter of the coil varies with how far along we are in this particular winching operation, which in turn mean you want to really have careful control over the speed. Okay, this last example, have a picture of a crushing or screening machine on the screen, but it could be in any particular industry. Really, a couple of things that came across from system design engineers was how can I be sure that the sensor that I've got on let's say a valve is actually correct? How can I be sure that there is no flow going through that particular part of the circuit? If we're measuring the flow rate, maybe to monitor the pump health, but we're also measuring it to tell us from a safety point of view whether we have any flow in the circuit. So as a secondary safety function, it's invaluable to actually know not that the valve itself says there shouldn't be any flow, but actually by measuring flow in the circuit, we can tell whether there is any flow present. The other area that's we've been talking to customers about, and particularly in the mining sector, they're looking to how to remove the technician from the machine, particularly when it's operating. In many things on a hydraulic machine, it's very difficult to go and set them unless the engine's running and the hydraulic circuit is running as well. But that means that the person who may be adjusting a relief valve, adjusting another component on the machine, has to be right inside the machine, really in the dirty, hot environment, in order to make that change. That may also be true that if you want to go and test that pump, like we showed in the picture earlier, that you have to put yourself in a not ideal position in order to do that. And so that's that drive, which we're seeing some of the mining companies and the mining construction machinery companies talking about, is that elimination of live work. How can you put a service engineer in a safe place while also doing the best job possible to maintain that machine? And ideally, to do that, you don't want to have to be right in a hot, dirty place right next to the hydraulic pump while you're doing it. If you can have the flow meter built into the circuit, already connected to the network that's there and standing remotely from it, then you've also made the system safer. So we see the example of the flow meter mounted straight up to the pump or prior to a motor. So just perhaps 1, 2, 3 things on the differences really between the standard flow meter that we started off with for an industrial test bench used in perhaps a benign environment, and that transition, if you like, through Make It Blue to a robust, rugged device, a monitor specifically for on and off highway machinery. Clearly, EMC compliance really important with all of the different noise that's on that machine. Protection from the elements, from water spray, from steam cleaning. Using standard connectors which are used in that industry also help with the IP rating. Dealing with vibration, and overall just a rugged and compact design altogether, which can bring these benefits. And I say the challenges that the customers have been speaking to us about have been around reducing downtime, monitoring the health of a pump, improving safety, monitoring machine component efficiency, also improving control and reducing warranty. So last couple of slides really just to reflect back on those challenges that say the customers brought to our attention right at the beginning. We believe that the CTA and this sort of innovative way of flow monitoring can help with all 6 of these. Exactly how it's implemented depends a lot on the hydraulic circuit, but we believe it's got a role to play really in reducing downtime, helping monitor cycle times, reducing warranty, involved in that discussion around power by the hour, looking at energy efficiency, closed loop control, and the elimination of live work and improving machine safety. So that's it. I'm just looking at the clock. I think I've just about burnt through the 45 minutes that we had set. Go on to any questions. I just see something pop up there.
There was. I've just, yeah. Paul Marvin has just said, can you share anything about accuracy during vibration?
No, I don't have a graph that says under this vibration the accuracy goes like this. So essentially, let's talk about accuracy for a moment. If we're on a hydraulic test bench testing a pump or a valve, the flow meter that I showed right at the beginning would be calibrated for absolute accuracy. You'd be looking at sort of 1% indicated reading over the vast majority of its range. It'd have no problem maintaining that. What came across from the customers we spoke to is the ultimate accuracy is less important than the repeatability. So the CTA has what we've given it a notional 1% full scale accuracy. So if it was a 300 litre device, plus or minus 3 litres over the whole of its range. And that being because we're monitoring all the time, we're seeing what's happening now compared to what happened yesterday. In terms of how vibration affects that, well, we've tested it to an SAE standard, and off the top of my head, I think it's standard 1455, which is the standard which most hydraulic components will be tested to for mobile machinery, and that has within it a certain vibration test, and it's passed that. So we would expect it to operate to better than the 1% full scale accuracy under any of those vibration conditions that are detailed in that spec. So I don't know whether that answers the question, but we believe that it's immune to vibration within that range.
I don't have anything else unless anyone's got anything else they want to ask now. I can't see anything else pop up.
There's another hand raised there,
there's
Sam.
a hand. Okay, I'd like to know how long time we need to do a maintenance.
So I guess that question, perhaps asking how often you need to take the flow meter off and get it checked, recalibrated. Our aim is for fit and forget. It will come down a little bit to the maintenance schedule on that machine, but really the biggest danger to the flow meter would be contamination. But that's also true of the pump and many of the other valves in that circuit. So as long as the contamination levels, the cleanliness levels in that circuit are maintained, let's take a NAS level of say 5, something like that, or the ISO equivalent, then really the main wear part in that is the bearing and the turbine, and that shouldn't be affected as long as the system is being kept clean. We've been operating these units on a few machines now continuously for probably heading for a couple of years, and we've not had anything go wrong with them in terms of the actual device itself. We've had other things happen to them on the outside of the device where the customer has unfortunately done perhaps not some ideal things, but that wasn't actually to do with the design of the flow meter. It would happen to anything. But so the flow meter itself, we're designing this as a component, not as an instrument that you would send back every year for recalibration, like perhaps you would on a test stand.
One more. Can the unit withstand a reverse flow?
Absolutely, yeah. Bidirectional, fully accepts flow in either direction. It will measure flow in both directions. It's not adversely affected by flow in either direction.
Can't see any more, and if no others come through. If you've got one you want to unmute and ask, then go ahead. Oh, very good job, Martin. Well explained and presented. Not so much a question, but a statement.
Should we go on to the just the last couple of links there, Sam? And
yep, finish off. Yeah. If you have any other questions you can think about afterwards, then you can get in contact with us. And we've got one portability. Sorry, one last one.
Perhaps you could expand a bit there, Michael, on portability.
just while we wait for that. So,
or if sorry, Sam, if Michael,
on.
I don't know whether you feel happy to come off mute and.
Yeah, I'm not sure how. Let me find people. Let me I'll find, this is me showing how to not know how to use Teams.
Yeah, I think you're off mute, Michael.
Yeah, he's unmuted. Under the technology.
I think there may be an issue with your microphone. We can't hear you.
Yeah,
Michael.
no, I can't hear anything.
I mean, in terms of portability, I could take that a couple of different ways. I mean, ultimately, this is meant for permanent installation. It weighs around about 1 kilo. It's not a particularly heavy unit, particularly as we've now made it as compact and as small as possible. And we designed it, I guess, to go on as many different on and off highway mobile machines as possible. So from that point of view, it's very portable. Together with the portable data recorder, we have got an example where, I don't know if you're familiar with our range of data loggers. We have the HPM 7000 range of data loggers, which accept both some analog signals and CAN signals, and can also accept J1939. And we have got an example there where I think the NFPC, amongst other places, have been testing that out, where they've been feeding the data into an HPM 7000. So you could indeed do that as well. So if you didn't have a data recorder or a PLC already built onto the machine, you could temporarily install it, take an HPM 7000 and feed the signal into that. Okay, good. We've answered that question. Thank you, Michael.
Excellent. Okay. Well, yeah, thank you for joining us. As I mentioned at the start, I've got an email to put together, including a survey and lots of links that will link to some of this stuff and some other of the information we have on the website. Also, if you want to keep in touch and you don't already hear from us, you can sign up to our newsletter here. Again, that link will be provided, and you can connect to us on LinkedIn if you don't already. The newsletter, we send out a quarterly newsletter which contains lots of this information as well. So hopefully we find it interesting. And again, I'll send all that out. You should get an email from Teams with this recording in it. If you haven't, please let me know. This is the first time we've used this system, so we're learning, and I just want to make sure it all works properly. But if not, I can share the recording with you. But
and that would be to what? That'd be, what's your email address, Sam?
Yeah, that's a good point. You'll hear from me. You'll get an email. Everyone on this call will get an email from me, and that will have everything on it. So you can reply to me if you don't receive anything. But I hope it works. So yeah, thanks for joining us. Thanks, Martin. Again, I think that's the third time I've watched it or heard it, but it's still interesting every time, and interesting to see the changes. But yeah, so again, we'll aim to do another one in February. We shall keep you posted. One of the questions on the survey is there any topics you're interested in? So if there's anything you think we could help with or like to hear about, then let us know.
Perfect. Thank you, Gary, for that feedback.
Yeah, thank you. Yeah, thank you, Gary.
We've covered such a wide range, Florida,
yes,
all the way through to, I think I might have seen someone from Australia. So
it'll be interesting to see where everyone's from on the report. So yeah, okay. Well, thank you very much. Martin, did you got anything else?
No, that's it. Thank you very much. Appreciate you spending the time with us.
Yeah, thanks everyone.